And this is something that we have done in the past. It's called Pascal's triangle. So if you have something like this, a plus b whole squared, you can always FOIL this like this. So that's just a plus b multiplying by itself. And then when you FOIL it, you do a times a times b times a, and b times b, and then you'll get this. You can also use the square formula. A plus b whole squared is equals to this trinomial here. So squared is pretty simple, but it gets a little bit convoluted when you're doing cubes or when you're doing to the power of 4, because at that point you're foiling it 4 different times and it just becomes tedious and there's a lot of room for error when you do something like this. So the traditional method is not preferred when we're expanding higher degree polynomials. So like power 4, power 5, power 6. So what do we do in that case? In that case, we would use something called Pascal's triangle, which gives us Pascal's triangle. All it gives us is the Pascal's coefficients is what it gives us. It gives us the coefficients and it gives us the number of terms as well when we expand those brackets. It looks like this. At the top of the triangle, there's always a 1. Underneath it, you have 1, 1. Underneath it, you have 1, 2, 1. Now, the first level, that just represents a plus b to the power of 0, which is always a 1. The second level, it represents a plus b to the power of 1, which becomes 1a plus 1b. And this is what the Pascal's triangle gives you. It gives you the coefficients. The third level, we have a plus b squared. It's going to look like this. You take your first coefficient, and it's going to be your first term inside the bracket, a, to the maximum power, 2. There's going to be no second term. And then it's going to be the second coefficient there of 2. It's going to be the first term's power 1 less. So we started with a squared, so it's going to be a1. And then b didn't exist before, now you get b1 as well. And then finally, it's going to be coefficient of the second term is 1 and b squared, like that. So that's a plus b whole squared. These are the coefficients of the terms. And then for the powers, you kind of have to think of it in terms of the maximum power and minimum power. It always starts with the maximum power of the first term and then goes 1 down until it completely disappears. So the next level would look like this. This represents a plus b cubed. So that would be 1. That's your coefficient of your first term. A to the maximum power, b doesn't exist, plus. Move on to the next coefficient, 1 power less, and now b exists. B comes into play, b power 1. And then the next term is again 3, a power 1 power less. It's always going in descending orders in terms of the powers of a. So 3, 2, a power 1, and b becomes power 2. And then finally for the last term, it's 1 b cubed. We can keep going. You can keep going till infinity. Okay, what does this represent? It represents a plus b to the power of 4. What will that be if we follow the same pattern?
One a to the power of 4.
What's next? Then you take your second coefficient, 4.
Plus 4.
What's the power of a? It's always 1 less, so cube.
Just 3.
And then b comes into play, 1. And then you keep going, 6a2, b2. Now b's power goes up, plus 4a1, b3, and then finally 1b4. And there we go, we've expanded this. And see, it's much easier to do it this way than having to FOIL it 4 times. That's tedious. And it doesn't always have to be in terms of a plus b. Here, let me show you an example. It could be something like 2a plus 3 over 2b to the power of 4. Now the idea is the same. The first coefficient of 1 times the first term to the maximum power plus coefficient of 4 times the first term to 1 power down times the second term to 1 power up plus 6 times 2a squared 3 over 2b squared plus 4 times 2a times 3 over 2b cubed plus 1 times 3 over 2b4. 3 over 2b4, like that. So it doesn't always have to be a and b. It can be 2z or 3 over 2k, whatever. But the idea is the same. First, this is your coefficient. It's always going to be the first term to the maximum power, and it keeps going down, one less, until it completely disappears. For the second term, starts out with nothing, does not exist in the first term. Technically, it does exist. It's b power 0, but that's a 1, so we don't have to write it. The power of b there is 0. Then from here, it goes up and up and up. So this is Pascal's triangle. Now we have power 6. We're going to use their triangle if they've given us. They've given us the triangles. They've given us till 5. We'll just build from this. So that's power 6. So again, remember, it starts from 0, 0, 1, 2, 3, 4, 5. This number here represents the power. So power 6 does not exist yet. We have to build it. We just have to go one more level. So there's always going to be 1s on the very outsides, like this. And on the insides, you add it like this. So 1 plus 5 is a 6. 5 plus 10, 15. 15 plus 10, 20. 15, 6, and 1. So there we go. Those are our coefficients. So what is going to be this thing expanded? So you start here. So the first coefficient is a 1. Then you take your first term to the maximum power, like that. And that's it. That's for the first term. There are 1, 2, 3, 4, 5, 6, 7 terms in this expression when we open the bracket. The next term will have a coefficient of 6. What's going to be the power of x?
5.
5. And now y comes in, y1. Now the next term would be 15x what?
4.
4. What's the power?
Y2.
Y2. And then you keep going. It's easy as that. X3, Y3. The powers, by the way, will always add up to the maximum power. So here, 5 plus 1 is a 6. 4 plus 2 is a 6. 3 plus 3 is a 6. The next one would be 15x2y4, 6xy5, and then finally 1y6. And there you go. That's the expression expanded. So now the next question here doesn't have the y, but nothing changes really. So we're looking at power 5. So we are looking at this line down here, because these second numbers always represent the power. So this is power 5. We're going to be using this line. So what's the first term?
X to the power of 5.
What's the second term?
5x to the power of 4.
Okay, anything else? So remember, the power has to add up to 5. Right now you only have a power of 4. 5x to the power of 4, and now you introduce the second term. Now the second term here, you can treat this as -2. You can treat that as x plus -2 to the power of 5. So your b here is -2. So it'll be -2 to the power of 1. 10x3 times what? What's the missing term here?
-2 to the power of 2.
And then you keep going. 10x2, -2 cubed, 5x1, -2 to the 4, and finally 1 times -2 to the 5. Now this one says simplify, so you can go a level deeper here. 1x5 is just x5, can't really do anything with that. But look at this term. -2 to the power of 1 is -2, times 5 is -10. So this entire term becomes -10x4 plus -2 squared is 4. 4 times 10 is 40, x3. What's the next term? If you simplify this, -2 cubed is -8, times 10 is -80, and x squared, right? -80, x squared. What's the next term? That's 16. Positive 16 times 5 is 80 as well. And then you just have x, and then the last term is 32. -5 is 32. So this is the thing expanded and simplified. As you can imagine, this is much easier than doing this 5 times. No one wants to be doing this, right? This is way more powerful, so don't foil this. Same idea here. It looks tricky, but it's really not. You have that tree right there, the triangle, and you just follow it to the appropriate level. Here we're doing 3, so we're looking at this row. What's the first term?
5x to the power of 3.
So it'll be 1 times 5x cubed. Now that cube applies to the entirety of 5x. Plus, the next term is 3 times 5x squared times 2y1 plus 3 times 5x cubed. Sorry, not 5. I need to go lower. So it's going to be 5x1, 2x squared, and then the last term is 1 times 2y to the maximum, b cubed. The second term to the maximum power. What is 5x cubed when you expand this? What's 5x cubed expanded?
It's 125x.
125x to the power of what?
3.
3. So there you go, that's your first term. Now look at the second term. It's going to be 3 times 5 squared, so that x, power of x is x squared, power of y is a 1. So those are our variables, and now we got to look at the numbers. 3 times 5 squared, so that's 25. So 3 times 25 is 75, times 2 is 150. So you group up the numbers together, you group up the letters together. So that's going to be your second term. The third term, power of x is a 1, so it's just going to be x. Power of y is a 2, so it'll be x y squared. And then you multiply the numbers. 3 times 5, 1 is 15, times 2 squared is 4. So we have 15 times 4, 60. And what's our last term when we expand it?
It's 8y to the power of 3.
Correct. And you're done. Cool?
Mm-hmm.
Is this difficult?
No.
So if you ever see a expression like this, use the triangle to solve it. And the triangle is very easy to make as well. Always starts with 1, 1. There's always going to be 1, 1s in the edges. And then you just combine the middle term. There's always going to be n plus 1 terms in the expression when you open it, where n represents the power. So there are 3, if the power is 3, there's going to be 4 terms. If the power is 4, there's going to be 5 terms. So this one is definitely everything outside the box. So we're given the 12th row. So we're building it and we're given the 12th row. So you have 1 here, 12, 66, 220. This is the 12th row. These are the coefficients, Pascal's coefficients. The question is asking us, what are the first 4 coefficients of the 13th row? Remember, it always starts with a 1, right? So there was a 1 up here, there was a 1 up here, which means on the 13th row, there's going to be a 1 down here. So that's our first entry. Our second entry is going to be the sum of these 2 terms from the previous row. So that's going to be 13th. So that's our second entry. What's our third entry?
78.
And the last one is again, whatever that is, 286.
Mm-hmm. And then 1.
No. 1 is going to be all the way over here. There's going to be 14 terms here. We don't know these guys,
Oh, okay.
right? Because 13th row, there's going to be 14th term. Yeah, there's a 1 there, but we don't know what these guys are. We're going to need this. All of these are pretty simple. Maybe we'll try doing this one. Maybe we'll do it for a little bit less power because the idea is the same. Let's do it for cubed. Let's say you want to open this. For cube, it's 1, 3, 3, 1, the coefficients. Our question is, how do you open something like this? So far, everything we've seen had 2 terms, but this one has 3 terms. So the way to do this is to group either 1, 2, this, and this, or you can do 2, 1, this and this. So I'm going to group it as 1 and then 2. By that, I mean y plus z is my b and x is my a. So x is my first term and y plus z is my second term. You can group x plus y as your first term as well. Nothing really changes. The final answer will be exactly the same. So again, start with your first coefficient, 1. Then you take your first term, x to the maximum power, plus your coefficient. Now your first term drops by 1, the power. What's going to be your second term here?
Y to the power of 1.
So remember, y plus z is b now.
Mm-hmm.
So it'll be y plus z to the power of 1.
1. Okay.
The next term would be 3x1 y plus z squared. And the last term will be 1 times y plus z cubed, like that. Cool?
Mm-hmm.
And then you FOIL it from there. I guess you have to use, so that by itself is 1y3 plus 3y2z plus 3yz cubed plus z3. That's squared there. This by itself is y squared plus 2yz. Again, you have to use the Pascal's triangle again for this and for this. So your final answer will be x cubed plus 3x squared y plus 3x squared z plus 3xy squared. Just multiply all three of these terms with 3x plus 6xyz plus 3xz squared plus y cubed. So there's going to be many terms here because we have Pascal's triangle within a triangle. So if you have 3 terms, you'll end up getting actually 9 terms instead of the usual 4. So that will be the final answer for this question. It's a little bit tricky because we have a triangle within a triangle. All right, so that's Pascal's triangle. It's pretty basic, nothing too fancy. You can move on from there. Maybe we'll just do a quick review of this entire unit. It says determine whether it's arithmetic, geometric, or neither. Remember, if it's an exponential, it is going to be a geometric function. Look at A. What kind of a function do we have there?
Exponential.
So that arithmetic or geometric?
Geometric.
Yeah, you don't even have to check. What about B?
Arithmetic.
So B is going to be neither because that is a rational function. It's not a linear function. Arithmetic is linear, geometric is exponential. So this one, n cannot be -1/2. Otherwise, you'd be dividing by a0. It's a rational function. That's neither. What about C?
C is arithmetic.
Yeah, because it's just a linear function. 5x goes through the origin with a slope of 5. What about D? I can always write it out. So the next term is going to be the previous term times 5. So 5, sorry, not 5, times 7. So 7 times 5, 35. 35 times 7, 245. 245 times 7, whatever that is. But the next term is always the previous term times a 7. Is that arithmetic or geometric?
Geometric.
Yeah, because T1 is 5 here, T2 is 35, so all the way here, and T3 is going to be 245. That's definitely not linear because the next term you're multiplying by a common ratio r. 7 unchanged, that's going to be an exponential function, it's geometric. For E and F, we need to actually write it out because it's not quite clear cut. So for E, the next term is 1 minus the previous term. So we have 19. So 1 minus 19 is -18. 1 minus -18 is 19. 1 minus 19 is negative 18. So you have this pattern. What is this? Linear, exponential, arithmetic, geometric, or neither?
Neither.
Neither is correct. Cool.
Mm-hmm.
Okay, for this one, the next term uses what? The next term uses the previous two terms. Okay,
Mm-hmm.
so let's look at this. T3 is 2 times the previous term minus 2 terms 7. So previous term and the term before. So T2 and T1. T3 would use T2 and T1. T4 would use T3 and T2, like that. So that's 26 minus 7, that's a 19. T4 would be 2 times T3 minus T2, like that. So that's 38 minus 13, that is 25. This will be 2 times 25 minus 19, 15 minus 19, 31. So we have 7, 13, 19, 25, 31. Is that arithmetic or geometric?
It is arithmetic.
Yeah, it is, because you're just adding what each time? How much are you adding?
6.
6, yeah. So that's your common difference, D. So for this one, it says determine the general term. The general term for an arithmetic sequence is this. The general term for a geometric sequence is this. And it also says the recursive formula. The recursive formula usually for a arithmetic sequence is the previous term plus or minus some D value. Or geometric, it'll be the previous term multiply or divide by some common ratio. So for A, geometric sequence, we have A is -9, R is -11. What is the general term for this? So you just plug it into this formula. A is -9, N we don't know. That's the thing about general term. It's always going to be in terms of N. And our, that's the wrong formula. Geometric sequence, I should be using this one. So A is -9, R is -11, and N we don't know. So there we go. That would be the general term. And for the recursive term, it's just going to be the previous term times what?
Times R.
Yeah, so -11. So the next term is the previous term times -11. That's the answer to part A. You're done. General on the top, recursive on the bottom. Part B appears to be a little bit more complicated because we don't know A or D. So we know T2 is 123, and we know T3 is -456. Is the D positive or negative here, the common difference? We had 123. We added or subtracted some number to this. that gave us 456. So is D positive or negative?
Negative.
Yeah, negative. What is the D value?
Negative 333.
So we have 123. We subtracted some number from this and we got negative 456. In other words, 123 minus x is equals to negative 456. So x, the term that you subtracted, will actually be 123 plus 456. It's going to be 579. So you actually subtracted 579 to get that. So your D is 579, which means if we go one level here, if we add 579 to 123, we would get our first term A, right? Because we must have subtracted 579 from our A to get this. So just add 579 to this. That will give us our thingamajig, our A value, 702. So we have everything now. A 702, D is negative 456. Sorry, not negative. It's D is negative 579. So your general term is A plus n minus 1 times negative 579, where A is 702. So that's your general term. Your recursive, what do we do with the previous term to get the next term? Do we add or subtract?
Subtract.
Oh yeah, we subtract 579. There we go. That's one way of doing this. The other way of doing this would be that you turn this into a system of linear equations. T2 means A plus 1D. That's 123. T3 means A plus 2D. We're just plugging it into this n minus 1, so 3 becomes 2. Like that. And then you would want to subtract your A's. You get negative D is 579, so that means D is negative 579. So that's how you can find your D value. Plug it back in here to get A value of 702. So that's an alternative way of finding your A and D. This was probably easier here because you're just talking about the first few terms. But if they're talking about 7th term or 12th term, then this would be way more powerful. The next one says, determine the number of terms in each sequence. So now the n is missing, right? The n is missing. For A, is that arithmetic or geometric? It is going to be an arithmetic sequence, right? You're adding what each time?
7.
7. So we know A is 18. We know D is positive 7, the common difference, but now the n is missing. But we do have Tn, T here being the last term, 193. So Tn is A plus n minus 1D. Tn represents the last term. It's 193. That is equals to A plus n minus 1 times 7. How do we solve this expression for n? It's just a linear equation.
You subtract 18.
All right, so that's going to be 175 is equals to n minus 1 times 7.
And then you divide by 7.
So that's 25. And then you add 1, so it's going to be 26. So this is your 26th term. So there are 26 terms in this sequence. The next one is the same thing, except it's geometric because you're multiplying by what? What's the D value for B? Not D, sorry, R.
-5.
Yeah, -5. So Tn is A times R to the power of n minus 1. Tn is this number, -156,250. A is 2, R is -5 to the power of n minus 1. How do we solve this exponential equation?
You divide by 2.
Yeah. And then what?
You do logs.
Yeah, you do logs. So log of -78125 is equals to n minus 1 times log of -5, yeah?
Mm-hmm.
The thing about logs is that it does not do negative numbers. Log function looks like this. Let me see, -78125. Yeah, it doesn't do logs. You get an error when you plug this. So the log may not work out here. What we need to do is this. We need to rewrite this in terms of -5 to the power of. That 78,000 expression. We need to write it in terms of -5. So it just becomes a guess and check. I'm just going to do -5 to the power of 8. Cannot be 8 actually, because then that would give you a positive number. Must be an even number. Sorry, must be an odd number up here. If this was even, then you would always get a positive expression. But this is negative, so we know that number is odd. So let me do -5 to the power 7. And that's exactly what it is. It's 7. So -5 to the power 7, like that. Now what? If they have the same basis, you're allowed to cancel them out, yeah?
Mm-hmm.
Like if you have 2 cubed as 2 to the power of x, x would be 3. Same idea here. This base and this base cancels out. 7 is n minus 1, therefore n is 8. That's your 8th term. There are 8 terms in this sequence.
Mm-hmm.
That makes sense? So the log didn't
Yeah.
work here because of the negative number. What's the difference between a sequence and a series? The difference is that series is just either the sum or the difference of a sequence, okay?
Mm-hmm.
It's either the sum or the difference of a sequence. So if we just put this as plus or minuses, then that would be a series. The thing about series is that it actually, the goal of series, we're not going to get into it too much, but when you do take calculus later, it's a very powerful tool to see whether a sequence diverges. Diverges means goes towards positive or negative infinity. This is called diverging sequence. So for example, 1 plus 2 plus 4 plus 8, you're multiplying by 2 each time. You can notice that this, when you add them up, right, it's going to keep on increasing and increasing and increasing, yeah?
Mm-hmm.
So this is an example of a diverging series. It'll go towards infinity.
Mm-hmm.
But what if we do something like this? And we're not going to get into too much. This is going to be very hard to tell whether it's diverging or not. We need to use some calculus. What if we had something like this? Where A is still 1, R is still 2, but now the only difference is that the sign flip-flops. You see this?
Mm-hmm.
Now, is this diverging or is it converging to a certain number? We don't have the tools to answer this just yet. So that's basically the point of a series. Well, you can, it's gonna look weird, but you can rewrite this. I don't know what the series is for this, but every sequence you can write it as a series. And sometimes it uses like trig functions. This is not the one for this, but this is an example. You can rewrite a series in terms of a function like this.
Mm-hmm.
And then you use calc to see whether this converges or diverges. And that will help us answer this. I think this one converges. I'm not 100% sure. Every series basically you can rewrite it as a general term. Not every, I guess, but for the most part. Okay, we have 15 minutes left. Let's see this one. So your grandparents put aside $100 for you on your first birthday. So you were born, this is your bank balance, you had nothing. On your first birthday, you have $100. Every following year on your birthday, they put away 75 more than they did the previous year. So how much are they putting in on your second birthday?
175.
Yeah. Yada yada.
Mm-hmm.
The question is, how much money would you have accumulated by the time you're 21? So that's the question. Is this arithmetic or geometric?
Geometric.
Okay, how? How is it geometric? What number are we multiplying by to get the next number each time? Because 4 would be 325, 5 would be 400. Are we multiplying something or are we adding something each time? 75 more than the previous year. Think about it that way. 75 more.
We're
Is that
adding.
yeah, we're adding, right? It's a plus.
So it's
More just means
arithmetic.
it's arithmetic. So our first term is 100. T1, right? A means T1 is 100. What's our D?
75.
75. Now this next part is very important. Are we looking for T21 or are we looking for S21?
S21.
Exactly. We're looking for the sum because we want to find the total accumulated value, right?
Mm-hmm.
So there's two formulas when it comes to sum. Both of them would work actually here. Both of them would work just fine. But one of them is easier than the other one, I think. Which one would you use, top or the bottom?
Bottom.
Okay, so to use the bottom, you need to know Tn, which means we need to know T21. Do we know that? No, we don't know T21. We could find it though, right? So if you want to use the bottom one, you'll first find T21 by doing A plus n minus 1, so 21 minus 120 times D, like that. So that's what, 1500, 1600, I believe is what that is. So you need to first find T21. So that's going to be 1600, and then you can use the bottom one. So S21 would be 21 times T1 is 100. Tn is 1600 divided by 2. So it's 21 times 100 plus 1600 divided by 2. That's 17,850. So that's the total amount you would have accumulated. I'm just going to show you that the answer would be the same if you use the first formula. So S21, if you use the first one, would be 21 times 2 times A. So that's 200 plus 20 times 75 over 2. So let's plug that in. 21 times 200 plus 20 times 75 divided by 2. That answer is exactly the same. So it doesn't matter which one you use. The answer will be the same, okay? Actually, the answer will be, it doesn't apply to this question, but practically in real life, it will be way more than 17,000 because you'll be getting your interest compounded year after year after year. Now, I can't tell you what it is. Let me think. Yeah, we don't really have a quick way of finding out how much it would be. But it would probably be something like this, 17,850 times 1 plus I to the power of n. So let's say your interest rate is 5%. So it's going to be 1.05 times 21. Again, this is just a rough approximation. It's going to be 49,729, almost 3 times as much. But that's just a rough approximation. But I think it'll at least be double, because of the interest rates and how they get compounded year after year after year. Let's go right back. These ones, I always find them tricky. Sometimes the pattern is very easy to see. Sometimes it's very difficult. This one, if you see it, the answer is in 5 seconds, you can get it. If you see it though, if you need to be able to see it. Do you notice anything about these patterns? I'll give you a hint. Well, that's basically giving away the answer, but TN
They're
uses,
just like adding them together, like 1 plus 7 is 8, and then
yeah,
7 plus
exactly.
8 is 15.
The next term is a sum of the previous 2 terms. So here, this will be what? 161 would be the answer to this, right? Let's add 23 to that. If you see it, it's very easy. This is called the, well, this is not the Fibonacci sequence, but that's where it comes from. Fibonacci sequence is this. You can just type this in Google and you'll see that a lot of things in nature actually follow the Fibonacci sequence. Ever wondered how a lot of things, naturally occurring things, are circular in nature?
Uh-huh.
Is because nature actually tends to follow the Fibonacci sequence. If you look at this sunflower shape, right? If you look at the galaxies, if you look at planet Earth, a lot of things are spherical because a lot of things in nature tends to follow this Fibonacci sequence. This is an example of that because Fibonacci sequence always starts with 1, 1. This one's fairly simple as well. What's the next term?
P6 minus 6 cubed.
Is it gonna be minus or plus though? If you look at the pattern,
Plus.
plus, it'll be plus. This one's very simple as well. And what's the next term? Again, treat it independently in the numerator and in the denominator. You'll see it. No? In the numerator, you're just subtracting 6. In the denominator, you're
And then
adding
it's
3,
adding
right?
3.
It's easy as
Mhm.
that. So it's going to be negative 5 over 18, negative 11 over 21, negative 17 over 24. That's it.
Mhm.
Easy peasy. But what if we make this a little bit difficult? What if the question is like, what's T100 for this sequence? Then what? No one has time to add them 100 times and come up with all of them. So let's see if we can find a shortcut for this. In the numerator, A is 25, D is minus 6, right?
Mhm.
So your general term in the numerator is A plus N minus 1 D. So it'll be 25 plus N minus 1 times negative 6. So that's it for the numerator. What about the denominator? What's the pattern there?
You add 3.
You add 3. So A plus N minus 1. Like that? Is that what you meant?
Mhm.
A plus N minus 1 D. Yeah, I think that's going to work. We can simplify this a little bit. So it'll be 25 minus 6n plus 6. And the denominator, we have 3 plus 3n minus 3. So this will be 31 minus 6n over 3n. So 31 minus 6n over 3n. So that's the general term for this. Let's check if that works. So 1, 2, 3, 4, 5, 6, 7, 8. So this was T8. So let's plug 8 in there. 31 minus 6 times 8 over 3 times 8. 31 minus 48 over 24, negative 17 over 24. So it checks out. Always double check your patterns, right? Sometimes
Mhm.
they may work out, sometimes they may not. But this one is just, you just do a linear function on the top and on the bottom. So it's not too bad. Cool.
Mhm.
All right, that's the last question that I had for today. We'll pick it up tomorrow.
Okay. Thank you.
So yeah.